the fifth lecture of our webinar series. And today we have one of the most distinguished professors from Australia, Professor Chennupati Jagadish. And I welcome Professor Shinu Thomas from our department to introduce the speaker to the audience. Welcome, madam.
Thank you, Praveen. A very good morning to all of you. And today we are extremely privileged to be having with us Professor Chennupati Jagadish from the Research School of Physics, the Australian National University, Canberra, Australia, to give us a talk on semiconductor nanostructures for optoelectronic applications. Professor Jagadish is a distinguished professor and head of Semiconductor, Optoelectronics and Nanotechnology Group in the Research School of Physics, Australian National University. He is the past president of IEEE Photonics Society. He is the editor-in-chief of Applied Physics Reviews, editor of 3 book series, serves on editorial boards of 19 other journals. He has published more than 950 research papers, holds 5 US patents, co-authored a book, co-edited 15 books, and edited 12 conference proceedings and 8 special issues of the journal. He is a fellow of 11 science and engineering academies and 14 professional societies. He has received many awards, including IEEE Pioneer Awards in Nanotechnology, IEEE Photonics Society Engineering Achievement Award, OSA Nick Holonyak Jr. Award, SOMIA Award, UNESCO Medal for his contributions to the development of nanoscience and nanotechnologies, and Lyell Medal from the Australian Academy of Science for his contributions to physics. He has received Australia's highest civilian honor, Companion of the Order of Australia, for his contributions to physics and engineering, in particular nanotechnology. With this brief introduction, I welcome you, Professor Jagadish, for today's talk. Thank you.
Okay, thank you very much, Professor Shinu, madam, for that kind introduction. First of all, I would like to thank Professor Pramod Gopinath for inviting me to speak to you today. And first of all, also, I would like to congratulate all of you for celebrating 25th anniversary of your school, and then it's really a pleasure to really know and be part of these celebrations. As been mentioned, that I'll be talking about semiconductor nanostructures and nanowires for optoelectronics applications. And in addition to being at the ANU, I also have honorary appointments in India and Japan and China and Taiwan and then US and UK. So again, it's a really pleasure for me to be associated with so many of my colleagues in various parts of the world. And before I proceed further, I would like to acknowledge my collaborators. And today's talk is really a collaborative effort between my group at the Australian National University and then work with many universities in Australia, collaborations with Australian universities, US, UK, and China, Sweden, Italy, Russia, Switzerland. So really, it's a really pleasure to work with my colleagues in various parts of the world. And I want to sincerely thank them and also many students and postdocs in those groups, those who contributed to our joint research. And for me, that's the most fun part of doing science, is that there are no national boundaries. We can all work together. And so that's been, you know, I've been enjoying working with all of them. I want to sincerely thank them. This is my group at the Australian National University, and then typically 10 to 12 nationalities at any one time, and then they're bright young people. And then it's really a pleasure to work with them. And then again, I want to thank them for their contributions to our work. And without their hard work, there's nothing much to talk about. It so happened that I also have got a student from your School of Photonics, Ashwini Gopakumar. And so she's in fact here in the front. And she's in the 3rd year of her PhD or so. And it's really great to have somebody from your university working in our research group. And I also want to thank our funding agencies for the funding they provide to us and allowing us to be able to have fun doing science. So here's an overview of my talk, and I'll give you the motivation why we're interested in these semiconductor nanostructures, and then how do we make these ones, and then also talk about a wide variety of devices which we are making using these nanostructures, and I'll draw some conclusions. So we work on these terahertz modulators and also using nanowires for photoelectrochemical water splitting, but I'll not have time to talk about these things, and I'm happy to talk to any of you if you're interested in offline. And also I would like to thank many groups, those who are working in the field of semiconductor nanowires all over the world. And in fact, we learn from each other, and it's really important to acknowledge our colleagues, those are contributing to our discipline. And I want to thank all the groups, those who are working in the field of semiconductors, semiconductor nanowires, enriching our field, and we're learning from each other. Before I proceed further with the nanowires, and then let me really introduce you to the various industrial revolutions. And then, as most of you know, that the mechanization started off with the steam power in the first industrial revolution. Second industrial revolution started with electrical power and with mass production. Third industrial revolution started with computer power and automation. And then now fourth industrial revolution, people are predicting that the digital world and then the biological world will be coming together in terms of a human-machine interfacing or so. And then the light is going to play an important role. As most of you know, that about 80 to 90% of our information is obtained through light. So that means light-based technologies are going to really play an important role when you're talking about human-machine interactions. Currently, light-based technologies are about $1 trillion Australian dollars. And so then the people are predicting by 2030, and then they'll be doubling. And that means there's an enormous amount of potential for growth of the optics-based technologies. So again, the World Economic Forum has identified that in 2018, so some technologies which are really needed for the future of the society, and they're talking about holographic displays, wearable optical sensors, and light navigation and communications using technologies like LiDAR, and then also 3D vision and gesture recognition, and enhanced machine vision and augmented reality. So all these technologies require smart miniaturized optical systems, and then you really need to develop the fundamentally new approaches, for example. So that's where we have got now funding for a Center of Excellence, which has been funded by the Australian Research Council. And then this has been directed by my colleague, Professor Dragomir Neshev. In this center, we are really developing nanoscale light sources like LEDs and lasers, manipulating light using metamaterials, for example, and also using nanostructures for detection of light as well. So if you want to have any optical system, you need to have all three components, and that's what we are really working towards, making really generating light and manipulating light and detection of light. And so really to develop some of these technologies like Li-Fi and then holographic displays and then LiDAR and those sorts of technologies. So 5 universities in Australia are involved in this particular Center of Excellence, and then about 15 CIs are involved. And really, again, it's a pleasure to work with my colleagues in various parts of the country. Also, there are about 20 different groups. Those are also working, joining from the international groups, participating in our center as well. And then, in fact, the center is planning to advertise for some PhD positions and postdoc positions. And if any of you are interested, and then please keep an eye on this website and then be on the lookout for the advertisements. So now let me talk about optoelectronics. What is optoelectronics? So, well, all of us know about electronics, and then silicon is the workhorse for the electronics. And today we are using a smartphone or a computer or any device, and the electronics is mostly made out of the silicon technology. But unfortunately, silicon is not a very good light emitter because of the indirect band gap nature of the silicon, for example. So you need to really have direct band gap semiconductors which really emit light. And those are the ones which are in the group 3 and group 5 of the periodic table. For example, 3,5 semiconductors, we call them gallium arsenide, indium phosphide, and gallium antimonide, gallium nitride, indium nitride. Combination of these elements, and I've got a different compounds form, and then these compounds have got different band gaps. So that means energy difference between the conduction band, bottom of the conduction band and top of the valence band is the energy gap. And then depending on where you want to have the light emission, you'll choose the right kind of semiconductor, and whether you want to have in the UV region or the visible region or the infrared region, then you just choose the right semiconductor or so. So in fact, the developments in the nitride semiconductors like gallium nitride, indium nitride, aluminum nitride has led to the development of this blue LED, which was a missing link among the primary colors. Earlier we had red LEDs and then green LEDs, but blue ones were missing. And due to the development of this nitride technology, and then these scientists, Dr. Amano, Dr. Akasaki, and Dr. Nakamura, they won the Nobel Prize for Physics in 2019. And then having these 3 primary colors allowed us to be able to make white LEDs. So that means nowadays you got a large amount of solid state lighting is taking place. And so also large area displays made out of these LEDs. In fact, this is a picture from the New York, in New York Times Square. where in the bright daylight also you're able to watch the TV because of the fact that these are high brightness displays or so. But also that, of course, the same materials can be used for making lasers of different colors as well. And then we and many other groups are working in these areas as well. So today I'm able to talk to you by using optical fiber communications. And again, the signals from my computer have been converted into an optical signal using lasers. And then you got an optical modulator, which is nothing but an optical switch. And you send the information on and off through an optical fiber. And then you convert this optical signal into electrical signal again using photodetectors. And again, we make use of these indium gallium arsenide phosphide materials, both for sources and detectors, because that's where the small amount of absorption and dispersion takes place at 1.3, 1.55 micron wavelengths. So these materials are able to really provide those, have got the appropriate band gaps, are able to provide you the light emission and light absorption characteristics. In terms of the other detectors, and for example, infrared detectors, and nowadays in infrared detectors, again, you can make use of these materials to make infrared detectors. They're used for night vision applications, biomedical imaging applications, and also in manufacturing. For example, if you're looking at the heat dissipation in the computer chip, and then you can see that you can do the infrared image while you're running this computer chip and be able to identify where the hotspots are. And then that allows the computer designers, chip designers, to be able to redistribute these transistors so that the heat is distributed uniformly, because heat dissipation is a major issue in the computer circuits these days. But also the world's most efficient solar cells are made out of these compound semiconductors. Nowadays, already people have exceeded 47% or so. And these are the so-called multi-junction solar cells. And these have been developed for the space applications for satellites. But then once the efficiency exceeded 40%, and then people started thinking about how we can use them for terrestrial applications, people have been looking at the concentrated photovoltaic systems, where sunlight could be concentrated to 500 suns or 1,000 suns at the focal point of this parabolic mirror. And then what you do is that you'd want to have the most efficient solar cells, and that's where 3-phase semiconductor solar cells also play an important role. We work on mainly these 3-phase compound semiconductors, and then I'll share with you how we are making use of them for making a wide variety of devices. Nanowires. Why we're interested in nanostructures and nanowires? So nanowires are seen as building blocks for the next generation electronics and photonics. So it turns out that whenever you try to grow the nanowires of one material on top of the other, the lattice mismatch is no longer an issue. Whenever you're dealing with the growth of the epitaxial layers, one semiconductor one on top of the other, you always have to worry about what is the lattice constant of the substrate and what is the lattice constant of the layer which you're depositing. There's a large lattice mismatch and dislocation starts forming, and then these defects are not very good for making optoelectronic devices. So in fact, if in this case, because of their nanoscale and 3-dimensional architecture, these nanowires either expand or contract depending whether they have got a larger lattice constant or smaller lattice constant with respect to the substrate. Without creating any dislocations, you can really grow these nanowires. So if the lattice mismatch is no longer an issue, in principle, you should be able to grow nanowires of any material on any substrates. For example, we and others have been looking at how to integrate 3-phase semiconductors with silicon, because silicon is a workhorse for the microelectronics industry, and 3-phase semiconductors are the workhorse for the optoelectronics industry. How do we really bring those two together? And then the hope is that we'll be able to make 3-phase semiconductor nanowires on silicon, which I will come back to. Also, you can make axial heterostructures because this green material is different than the red material. So that means you can create quantum disks or quantum dots within the nanowire so that you can get single photon sources and a range of things you can do. You can also make a PN junctions within the nanowire. So that means you can really inject current and the N-type carriers and the electrons and P-type carriers holes in a semiconductor. So by combination of electron hole recombination leads to, for example, making LEDs or lasers. And PN junctions are also needed for making photodetectors and solar cells as well. So you can be able to make a single nanowire based these devices, which I'll come back to. Also, you can create a radial heterostructures or core shell nanowires. And again, this red material is different than this pink material or so. So that means in principle, you'll be able to create a multi-layered structures on one top of the other. You can also create a branch nanowires, which really provides you the opportunity to be able to make 3-dimensional architectures of a wide variety of materials. So in fact, here are some of the examples from my own laboratory where we were able to show that we've been able to grow gallium antimonide on top of gallium arsenide despite large lattice mismatch. You're able to show that you can really get atomically perfect gallium antimonide Gallium antimonide is a very good material for infrared detector applications, for example. You can also make indium arsenide nanowire, in fact, nano branches, for example. These can be used as cantilevers or scanning probes and other things on top of gallium arsenide, which you're able to show. The stem is gallium arsenide, and then the branch is the indium arsenide, for example. Here we're able to show that these are indium phosphide nano trees, which are very good for energy harvesting applications, particularly splitting of water to generate hydrogen as a pure and a clean energy source also. Most recently, we started moving from nanowires into nanomembranes, which again, I'll come back and then share a little bit with you. So the most importantly, international technology roadmap for semiconductors, and these are the people, those who determine what technologies are needed for the next generation electronics. They've identified the nanowires as a key technology component for the next generation electronics. So that's why there's major research programs are going on at Intel and then IBM Zurich and other places. And in fact, the IBM Zurich has demonstrated indium gallium arsenide nanowire transistors on a 6-inch silicon wafer, and there they're able to show that you can get excellent performance from these things. So that means nanowires are going to play an important role, both not only for photonics, but also for electronics. And so that's why there's a lot of global interest. So if the nanowires are so much of interest, and then how do we really be able to make these ones? So then there are two main techniques which we use. One is called as a VLS growth process, vapor liquid solid growth mechanism, which I will come back to. Another technique is called selective epitaxy, and we use a technique called metal organic chemical deposition. So MOCVD, we call it, and then there's also alternative technique called molecular beam epitaxy, and molecular beam epitaxy also can be used, and then you can choose whichever the technique you want, and then depending on what facilities you got access to, you can choose those ones. So in this case, what we use is we use some metal catalyst, for example, gold nanoparticles, and you can buy these gold nanoparticles these days commercially from 5 nanometers up to 300 nanometers or so. We typically use 30 or 50 nanometer gold nanoparticles and put a droplet of this colloidal solution of gold nanoparticles on top of semiconductor substrate. For example, in this case, I'm showing an example of gallium arsenide. So then it turns out that the gold has got a melting temperature more than 1000 degrees Celsius. But once, if it reacts with the gallium or aluminum or indium, melting temperature of this alloy comes down to as small as 350 degrees Celsius. So that means once if you heat this one into an MOCVD reactor, put this one into an MOCVD reactor and heat it to somewhere between 370 to 500 degrees Celsius, and then what happens is that you are creating, in this example, gold gallium eutectic liquid, and then if it introduces the gases needed for the growth of gallium arsenide, for example, trimethyl gallium and arsine, these gases get incorporated into this liquid alloy, and then it gets supersaturated, crystals start precipitating out, and gold is always sitting on the top here. So this is like, if you start putting, sugar into water, and then you can dissolve the sugar into water till its solubility, and then if you exceed the solubility limit, and sugar crystals start precipitating out, and the same physics is happening here. So this work of Dr. Hannah Joyce, who is now an associate professor at University of Cambridge, and during her PhD at the ANU in my group, where she has demonstrated gallium arsenide nanowires, she developed something called 2-temperature growth process, where she is able to show that you can get a beautiful cylindrically shaped nanowires, and you can see the gold nanoparticle sitting on the top. This is a scanning electron microscope image, and then I'll show you the transmission electron microscope image. Here, close-up of this one, you can see this black, this one is a gold nanoparticle, and then the remaining one is gallium arsenide. And by using this technique, Hannah was able to show that not only we can get a beautiful taper-free and cylindrically shaped nanowires, also that we are able to get atomically perfect nanowires. And in fact, this electron microscopy was done in University of Queensland and Professor Jin Zhang's group. So these nanowires are about 50 nanometers in diameter, and essentially you can change the diameter of the nanowire by essentially changing the nanoparticle diameter. And we have demonstrated nanowires as small as 10 nanometers, as big as 300 nanometers using this particular process. And also we've demonstrated lots of other materials as well using this VLS growth process. Because we are incorporating a vapor into a liquid and getting a solid, and then this method is called as a VLS growth process. In the case of selective epitaxy, in this case, what we do is that we don't use any metal nanoparticles. We deposit some silicon dioxide on top of, say, in this case, I'm giving an example of indium phosphide by plasma enhanced chemical vapor deposition, or PECVD, and put some photoresist and electron beam resist, and then do the electron beam patterning of holes, formation of an ordered patterns of holes here. And then what we do is that we try to etch through this one to really expose the holes within the silicon dioxide, so that in these holes, indium phosphide is exposed, for example. Then you put this one into the emulsivity reactor and then heat it to somewhere between 650 to 750 degrees Celsius and introduce the gases needed for the growth of indium phosphide, trimethyl, indium, and phosphine. And then you can really create ordered patterns of these indium phosphide nanowires, for example. You can see this is, you can also see beautiful faceting formation of the hexagonal facets in the top view of these particular nanowires and beautiful ordered patterns here. This is work of Dr. Chian Gao, and she's now a research engineer in Blue Glass, a company in Sydney, developing some LED technology or so. So really, you can use either of the techniques. And again, in the case of selective epitaxy, where we have shown nanowires as small as 70 nanometers, as big as 700 nanometers or so. So you can really use either of the techniques depending on what you want to do. You can choose whichever you want. And in this case, because you created ordered patterns, you create ordered patterns of the nanowires. In the case of these gold nanoparticles, we have these are randomly distributed. That's why you end up getting these random distribution of nanowires. We can also create out ordered patterns of the gold nanoparticles and then be able to create ordered patterns here as well. And then we use both the techniques depending on what application we have. And these particular indium phosphide nanowires are 200 nanometers in diameter. So we've taken these indium phosphide nanowires and then excited with the laser pulse and look at the light coming out of these ones. And then we try to quantify the quantum efficiency of light emission as a function of the excitation power of the laser. And as you would predict that the higher the excitation power and the higher the quantum efficiency. And then essentially, then you can see the red curve is for the indium phosphide nanowires. And then the blue curve is for indium phosphide epitaxial layers, or the two-dimensional layers. And then they are both showing the very similar quantum efficiencies, indicating that we're able to get excellent quality indium phosphide nanowires. And then the surfaces do not play a significant detrimental role in the case, despite large surface area of these indium phosphide nanowires. And then these are very good for making solar cells and lasers and other things, which I will come back to. So we asked ourselves, instead of opening a hole in this mask, what will happen if you open a slot or open a ring? This is the work of my student who just finished his PhD, Dr. Nain Wong. And he spent about 3+4 years in order to be able to explore these things and then see what type of structures he can grow. Again, the same process of depositing silicon dioxide and putting some resist and do electron lithography patterning and of creating different shapes here. So again, he optimized various conditions in order to be able to get these things to work. So here's a case where when Nain Wong has opened up this slot along a particular crystallographic orientation of 101 bar, and then put this one into the emulsivity reactor and then introduce gases needed for the growth of indium phosphide. And you can see you can get a beautiful membrane structures, which are very thin structures also with this particular side facets of 101 bar 0 or so. But if you open this slot along another crystallographic orientation, 112 bar, and in this case also again, he gets the membranes. But in this case, these membranes are a bit thicker than these ones because there's some sort of a lateral growth takes place. And also that the facets are quite different facets than these ones, like a 112 bar 0 or so. But if you open the slot between these two extreme cases and then in between, and then you end up creating these beautiful diamond-like structures with these alternating facets of both types or so. So now suddenly you can see instead of just making nanowires, and then you can start going for nanomembranes, or thinner nanomembranes, thicker nanomembranes, or diamond-like structures or so. And again, a lot of work has gone into in order to be able to get these qualities, beautiful structures or so. So just to really acknowledge my students and postdocs, and so really the results which I'm sharing with you, and I might be flicking through in spending only 30 seconds on a slide, but students or postdocs have spent about a year or 2 or sometimes 3 years in order to be able to get these beautiful results. I want to thank them for their all their hard work. So then, of course, if you open this ring, and again, you can get these ring-like structures, and again, with alternating facets or so. And if you keep on growing, then what happens is that this structure keeps growing, and then it gets filled up, and then you create a nanomembrane, and then you keep on growing, and ultimately you end up finishing off with these hexagonal facets, because these facets are the lowest energy surface energy facets, and that's why they end up finishing off with these hexagonal facets also. And so really, it opens up a lot of opportunities for us to be able to do that. So we've gone off and looked at the luminescence properties of these ones. In this case, we are using cathodoluminescence. Photoluminescence is where you excite with the laser pulse and look at the light coming out of this one. In the case of cathodoluminescence, we use an electron beam to excite the electron hole base and look at the light coming out of this one in a scanning electron microscope. So you can see that these membranes on the top view and in the diamonds and ring-like structures here. And then here is the one where you can see that the very nice light emission from all these structures, very uniform light emission, indicating that really Nine Wang has optimized these structures so well, there are no defects and you can get a beautiful uniform light emission from these structures. And in fact, we are using these things for a wide variety of applications. For example, we are exploring these ones to use these ring resonators or ring resonator lasers, for example. In fact, a new student, Wei Wong, has recently demonstrated these ring resonator lasers, which in fact we just submitted that work to a journal and we haven't published that work yet. So now let me move towards the devices. Till now I've only spoken to you about the materials and then how to really make these ones and how to characterize them and how to get to some of the best materials or so. But now in terms of devices, so lasers, all of us have studied about lasers and we've been told that you need to have a gain medium, you need to have a laser cavity, you can put some mirrors, and you need to pump this gain medium so that you can really get over the losses in the cavity, with the absorption losses, scattering losses in the gain medium, or mirror losses which are taking place here as well. Also, we need to create so-called population inversion, and that's where the lasing takes place. So really, essentially what happens is that whenever the model gain of a particular optical mode is equivalent to the optical losses in the cavity, and then the lasing starts taking place. And in fact, this is a lasing threshold condition. Essentially what it is saying exactly the same thing. The gain need to be equal to the absorption or intrinsic losses in the cavity in the gain medium, and then the essentially the mirror losses, and that's what really determines when the lasing takes place. So it turns out that if you take a nanowire of the right kind of nanowire, if you shine light from the top, light starts propagating through this nanowire, and then light comes out from the both ends of the nanowire. And then essentially, of course, you have to choose the right kind of nanowire, and essentially these nanowires are acting like waveguides because these nanowires have got a high refractive index of 3.4 or so. The surrounding medium is 1, has got refractive index of 1. So that means really light tries to stay in the high refractive index medium. And so in the process, what happens is that light propagates through these nanowires. But also that the both ends of the nanowire act like mirrors because the refractive index of indium phosphide, for example, is 3.4, air is 1. So of course, refractive index difference will tell you the reflectivity at both ends. So that means if you get things right, each nanowire should act like a laser. I don't need to really put mirrors or anything of that sort, but all these 3-5 semiconductors are direct band gap semiconductors, and then they end up, they've got a gain because they emit very bright light and efficient light as well. So again, we have been working in this area for a long time and in fact demonstrated a wide variety of nanowire lasers. And the first gallium arsenide nanowire lasers were demonstrated by student, Dr. Drew Saxena, who is now at Imperial College. And then Dr. Chian Gao has demonstrated indium phosphide nanowire lasers. And Dr. Tim Burgess, who is at IP Australia, has demonstrated zinc-doped gallium arsenide nanowire lasers also. I'll not have time to go into all the details of all these ones, and I'll give you 1 or 2 examples. So again, Drew Saxena has gone and then did a lot of simulations of these FTDD, finite difference time domain simulations, of looking at various optical modes and then how the light propagates through these nanowires. It is an example of the case where TM01 mode in propagating through a 260 nanometer gallium arsenide nanowire. And then you can see that the field is really concentrated at the core of the nanowire, which is ideal for this particular one. So here is a case where Drew's simulations show the threshold gain for lasing as a function of the nanowire diameter for a nanowire, which is about 10 microns long, which is sitting on a glass slide, for example, because again, low refractive index substrate is important here so that you can confine the light to the nanowire. So as you can see that, if I'm only plotting not from 0, from 150, because threshold gain for lasing, if you want to go to smaller diameters, is so large, before you really get any lasers working, you start creating enormous amount of damage and melting of the material also. So Drew simulations are showing that you need to have somewhere between 250 to 300 nanometer diameter nanowires, and they are ideal in terms of being able to make these nanowires lace sort of thing. So that's why we started going from 50 nanometers or so to nowadays about 250 nanometer diameter nanowires or so. Again, he has done the peak gain as a function of the injected carrier density, and again is a threshold-like behavior, and which also threshold carrier density needed to make lasers to work is also dependent on the temperature. That's what you would expect, for example. again, to cut the long story short, and so then based on Drew simulations and Dr. Jenny Jiang, who is at Cambridge University now, and then really grew on these structures and transfer them onto a glass slide, and then drew in similar measurements. And you can see if you excite with the laser pulse and look at the light emission, initially what you see is a very broad light emission like a photoluminescence and like a spontaneous emission. And if you keep on pumping and then you get into amplified spontaneous emission, finally you end up getting lasing or so. You can see very sharp light emission, and also pinning of the spontaneous emission as well is also taking place. And you can also see the output versus pump intensity characteristics, and you can see threshold-like behavior here. Also log-log plot showing that this S-type behavior, which is confirming the true lasing is taking place. You can also see above threshold, you see a beautiful interference fringes because two coherent dipoles are emitted from both ends of the nanowire. And then in fact, Drew has done simulations and he's able to show that the simulations and experimentally measured interference fringes match very well or so. And again, these are the first gallium arsenide nanowire lasers operating at room temperature made in the world. So that's again, a lot of physics and the designing of the lasers has required and a lot of optimization of the materials growth. And finally, they really be able to characterize these devices. So all work together very well. And so anyway, just to give an idea, how big are these lasers? So really these lasers, are so small, and then I can put about 10 lasers within the width of your hair, and sometimes you can be as many as 20 of them within the width of your hair, along the length of the nano laser, for example, nanowire laser. So that tells you that how tiny these lasers are. So what are we using these lasers for? In fact, this is a joint work with my colleagues at the University of Strathclyde, Professor Martin Dawson and Professor Michael Stein and Professor Anthony Hurtado. And then what they have developed is called nanoscale transfer printing. In this case, what they do is that they come up with a PDMS stamp, and then they pick up the nanowire and then be able to drop it off wherever you want. And again, this is a technique which they spent a lot of time in optimizing and be able to develop this one. And then research fellow Dr. Ben Wilhaber has spent a lot of time in developing this particular technique under the guidance of these professors there. So here's a case where they transfer these nanowires, lasers of indium phosphide onto PDMS surfaces and polymer surfaces. For example, we want to use them for polymer optoelectronics and a range of applications, for example. So the IOP, you can see these lasers here, and then IOP is their Institute of Photonics, the institute name, and then they're able to beautifully transfer those ones. And then they pump these individual nanowires and look at the light coming out of these ones. You can see the light is coming from both ends of the nanowires, indicating that these nanowires are all lasing. And then this is a really gentle transfer process and you're not creating any damage. You may argue that you're really transferring onto soft surfaces like polymers, but what about transferring onto hard surfaces? That's exactly the question which I asked them, and that's what they've done. They've transferred them onto flexible glass, again, use it for flexible optoelectronics applications. And you can see the nanowires lasers here and here and here in the optical micrograph. And then you pump them and look at the light emission. Again, you can see the light emission coming from both ends of the nanowire. And again, threshold-like behavior. And then here is spontaneous emission, and here's the lasing taking place. And also sharp light emission, indicating that even on hard surfaces, you can be able to transfer them without creating any damage. It's a really gentle process also. So then we asked them, can you be able to locate these nanowire lasers into nano antennas using this transfer printing technology? This is the work of my young colleague, Professor Fang Ren. And so then she's now professor at Nanjing University in China, and she spent some time at the ANU with us. So she has been developing these so-called bullseye antennas for terahertz metamaterials applications. So then I asked her that, there's the aluminum antennas are here, and there's a gap. And then I asked her that, can we really put these nanowires, asked my colleagues at Strathclyde, can they be able to put these nanowires in the middle of this gap here? So that's what precisely they have done. And in this case, you can see that they're able to really locate these nanowires very nicely. And sometimes they miss those ones, but mostly they're able to locate these ones. You can see the close-up of this particular nanowire. There's a nano antenna here, and the nanowire laser sitting here. So when you do not have any nano antenna, light is coming from the both ends of the nanowire, because it acts like a Fabry-Perot cavity, and which I've already shown you the video of that particular one, how the light is coming from both ends of the nanowire. But whereas if you have got this nano antenna, and suddenly light starts coming from the vertical direction. So that means we're able to really do the engineering of the radiation patterns, and we're able to get vertically emitting nanowire lasers, and you can see sharp light emission and threshold-like behavior. And that means you're able to really now arrange ordered patterns of the two-dimensional array of these nanowire lasers, which could be used for facial recognition, to meta optics applications, to even holographic applications or so. So till now, I've only shown you the nanowire lasers, which are optically pumped. And but really ultimately people are interested in electrically pumped lasers. So this is a work of my student, Dr. In-Suk Yang, and now he came from Samsung and he has gone back to Samsung. Here he is working as a research engineer. And so really, in order to be able to make these electrical injected lasers or LEDs, and what you need to do is that you need to do the P-type doping, which I mentioned to you. You need to make a P injection, and he did the P-type doping of indium phosphide here. And then this yellow one is a quantum well of indium gallium arsenide, which has grown because quantum wells have got a higher gain than bulk materials. And then he coats this one with, grows this one, N-type indium phosphide on top of this one. You can see a beautiful structure here, and then a real SEM image of this one. And then he transferred this one to glass slides and then tried to make contacts using electron mimeolithography with gold titanium contacts or so. So then you measure the IV characteristics, and you can see that the IV characteristics looks like a diode-like behavior, showing that he's able to really make a nice P injections and able to make ohmic contacts and all these things. So then he injects current and look at the light coming out of these ones. So this is so-called electroluminescence, if you want to call it. So you can see that as and when you're injecting current, and you're able to get a much brighter light emission coming from these ones or so. Also, he sees two emission peaks. That's mainly because of the fact that the quantum well, which is formed on the axial direction here, has got a different composition and thickness than the radial quantum well, which has been created here. So that's why you end up emitting and getting the light emission from two different wavelengths or so. But again, these nanowires are emitting in the 1.3, 1.55 micron window region, which is a wavelength region which is important for silicon photonics as well as for optical communications also. So at this stage, you can see that you don't see any narrowing of the line width as you saw in the laser case, for example. You also don't see any threshold-like behavior here, for example. So indicating that we were able to make only nanowire LED, not a laser. So then you ask the question, why that is the case? It turns out when you're putting metals on top of this nanowire to be able to inject current into these nanowires, but then these metals also got large optical losses. You got a large optical losses, that means cavity has got a large loss. That means you have to pump it harder to be able to get lasing to take place. And then if you're pumping harder and then you generate a lot of heat reduces the gain of the medium. You have to even pump harder, then it becomes like a vicious circle or so. So now I got a new student who came from IIT Kharagpur, Nektar Gagrani, and then she is now trying to design and then look at developing the nanowires without any metal contacts in order to be able to really use things like indium tin oxide and other materials so that you'll be able to inject current but not creating too many losses or so. I hope that in a year or two, I'll be able to really show you electrical injected nanowire lasers, which has been a challenging problem, not only for us, for the rest of the world as well. So In-Suk, before finishing his PhD and started making a single nanowire LEDs, and he also tried to make nanowire arrays, LED arrays. And then you can see that he grows these nanowires, and then the challenge is how to make contacts to these nanowires. And then he tries to fill these with a polymer material, and then etch selectively the polymer by using plasma etching so that you can expose the tips of these nanowires, and then deposit some indium tin oxide, which is a transparent conducting oxide. And then you can deposit indium oxide on the top there, put some metal contact on the top and the bottom and inject current and look at the light coming out of these ones also. Again, he shows that you can see the IV characteristics showing that the diode-like behavior. And then also you can see that as and when you're injecting more and more current and you're seeing much more light emission coming from these ones. You can in fact look at the optical image of these ones. You can see you're going to higher and higher currents and you start seeing a very bright light emission out of this probe here, showing that he's able to really make these quantum well nanowire LED arrays or so sort of thing. So because of the fact that we're able to embed these ones into polymer materials, we're able to peel these things off very easily. And so that means you're able to use them for flexible displays. For example, Samsung and Apple and others are interested in using these sorts of nanowire LEDs for flexible displays for foldable phones and foldable computers and a range of things or so. So that's why In-Suk has spent more time in making these LEDs rather than focusing on lasers also, despite the fact that, of course, it has also not been easy and it's very challenging as well. So now let me move towards other systems. And I've told you about lasers and LEDs, terahertz radiation. Terahertz radiation, in fact, as you know that in electronics, we go from microwaves to millimeter waves. And in the case of optics, we go from ultraviolet light to visible to infrared. There was a gap called Terahertz gap for a long time. But then during the last 25 years, and people have been developing terahertz technologies, and in fact, we and others have contributed to this particular work. So why people are interested in terahertz radiation? It turns out many chemical molecules have got signatures in the terahertz parts of the electromagnetic spectrum. So here is a case of the signature of a spectrum from lactose, monohydrate, anhydrate, and all things. But also a lot of explosives have got signatures in the terahertz part of the electromagnetic spectrum. And also a lot of pharmaceutical drugs have got signatures in the terahertz parts of the spectrum. So that's why people are interested in studying these ones. And people need to develop the technologies. But also terahertz radiation is reflected by metals. So because, for example, nowadays, if you go to the airport and they send you to this cube, like a box, and essentially they are not using X-rays anymore because X-rays are ionizing radiation, but then really terahertz radiation is a non-ionizing radiation. That means it doesn't create damage for you because terahertz radiation is reflected by metals. You'll be able to pick this up very easily. Also, terahertz radiation could be used for biomedical imaging. For example, look at the cavities in the teeth here, and wireless communications where you can download information much faster and without any cables or anything of that sort onto your smart device. And also, terahertz radiation is important for the detection of water content in the leaves, so thereby farmers are not going and wasting their precious water and only water them whenever the crops need the water by using this terahertz technology. So just to remind you that 1 terahertz is about 300 microns in wavelength. It is really far infrared, if you want to call it that way. So in fact, this is a joint work with Professor Michael Johnson and Professor Laura Hertz at Oxford University. We have been working with them for a long time. And then there's also the work of my student Kun Pang, and who is now a postdoctoral fellow at Oxford now. So really what she does is that she takes one of these nanowires and makes some electrical contacts using electron magnetography after transferring onto a quartz substrate, because quartz is transferred to terahertz radiation. So then she excites these nanowires with a laser pulse to generate the photocarriers, and then comes with the terahertz pulse, and the electric field of the terahertz pulse separates these carriers between these two contacts. So that means you can measure the photocurrent as a function of time, and you can see it dealing with the picosecond time scales also. If you measure the current as a function of time, and then essentially you can really measure the electric field of extract the electric field of the terahertz pulse, and also conductivity of the material which you're dealing with. In fact, that's how we started this work, where we were using terahertz spectroscopy to really measure the electrical properties of the nanowires in a non-contact way. And then when we were doing these things, we asked ourselves, instead of using ensembles of nanowires, can we use a single nanowire and then be able to make terahertz detectors? Again, to cut the long story short, in fact, we were able to demonstrate a wide variety of nanowire terahertz detectors. And I'll share with you the most recent work where, and Kun Pang has spent during her postdoc, and be able to really do this one. These nanowires are really put in an orthogonal direction so that we can really measure the polarization result terahertz detection also. So again, you can see the close-up of this electron microscope image. You can see these 2 nanowires are connected to these bow tie antennas, and also 2 nanowires are connected in the orthogonal direction. So the challenge has been to make sure that these nanowires are not touching with each other at this point where it is. And again, this work involves Oxford University and ANU, and also Strathclyde University. You can see the close-up of these structures, and you can see these nanowires here, and then the wire bonds and other things. So in fact, this work we just published last year in Science also. So what we're using these the polarization sensitive detectors, you can, for example, if you're looking at terahertz metamaterials, you try to send a terahertz pulse through these ones, and then terahertz pulse passes through this one and interacting with the metamaterials, and you'll be able to measure both an X and Y polarization, because that interaction leads to changes in that. You can see that these are the SEM pictures of the terahertz metamaterials Kun Pang has fabricated, and then she simulated that the terahertz transmission, and then for the X polarization and Y polarization should be like this, and based on her design, which she fabricated them, and then she goes and measures these ones using our polarization sensitive detectors, and then they show that both nice, beautiful horizontal and vertical polarization, showing that really very much comparable to what theoretically predicted or so. And now, we are really exploring to use these sorts of detectors for polarization sensitive, phase sensitive, and amplitude sensitive detectors, not to be able to create high resolution imaging terahertz systems also. So now let me move towards the last but one topic of the solar cells. And again, solar cells, nanowires are very interesting for solar cells. And one of the unique things with the nanowires is that the nanowires can act like light funnels, because nanowires have got a high refractive index of 3.4 or so. So that means, light likes to go into these nanowires and act like a funnel or light concentrator. But also that you can really decouple the light absorption pathways and carrier collection pathways for the first time using nanowires. When you're making a thin film solar cell, you need to make a PN junction and make it thick enough to absorb all the sunlight, and then carriers need to migrate long distances. And if you say that 20% efficient solar cell, that means 80% of the photogenerated carriers have been lost to defects or impurities and surfaces and other things. But whereas in this case, you can make the nanowire as long as you want to absorb all the light, and you can create this so-called core shell PN junction. So that means carriers can be collected efficiently. And also these nanowires also act like anti-reflection coatings because they got low reflection losses. So again, we did a lot of simulations and of what should be the height of the nanowire, what should be the diameter of the nanowire, what should be the pitch between the nanowires, or the diameter distance between the nanowires or so. And you can see here the photocurrent generated is mostly happening in the tip of the nanowire, indicating that you don't need to really make nanowires very long. About 1 or 2 micron long nanowires are more than sufficient in order to be able to really generate most of the current. And again, the nanowire diameter should be somewhere between 150 to 160 or so, and diameter to pitch ratio should be around 0.5 to 0.6 or so. So these simulations really play an important role in order to be able to really make these nanowire solar cells. And again, the challenge is how to make contacts, and again, fill these ones with the polymer material and etch selectively and put some indium tin oxide and then the metal contact at the bottom. And you can see the close-up of these structures also. So really, they cut the long story short again, and one of our colleagues at Technical University of Eindhoven, Professor Eric Baker's group, and then Professor Eric Garnett's group at FOM Institute in Emalve have demonstrated efficiencies of these nanowire solar cells as high as 17.8% or so, and which is looking extremely promising in terms of using these nanowires for solar cell applications. We have been exploring the possibility of using these nanowire solar cells for flexible solar cells, and by using the organic and inorganic semiconductors together in collaboration with Professor Terahertz's group at Oxford University. So in the future, you can potentially have flexible solar cells which can be on your backpack and are able to really, when you're walking on the street or so, they're really charging your electronic devices like phones and other things as well. So that's at least that's what our aim is, to be able to develop those sorts of technologies. So now let me finish off with the last topic. And I know that I'm running out of time. So this is the work of Dr. Vinnie Gautam, and who did her PhD from Jawaharlal Nehru Center in Bangalore. And then she came and joined my group, and now she's a lecturer in the University of Melbourne. So as all of you know that we got about 70, all of us have about 80 billion neurons, and then these neurons form into neuronal networks. So whenever you got a brain damage, what happens is that you end up breaking this neuronal network, and then you lose some of the functions. And whether you may not be able to walk or talk or move or what, anything can happen. So we ask ourselves, can we really create a neural patch and be able to make the connections back so that you can be able to make this neural network back to the normal state? So thereby you'll be able to really help people to get their functions back. So again, Vinnie has spent a lot of time in optimizing these things, and then she has grown these neurons on indium phosphide nanowires. You can see these nanowires from the top view here, and then it is a cell body soma here. And then these neuroids are really following these nanowire patterns beautifully here. You can see the close-up of these ones, and you can see the dendrites are also coming and following these patterns beautifully here. Instead of using a single neuronal cell, and if you put multiple neuronal cells, and this block, this dashed area is the one where you got these neuronal cells, you can see these axons and others are really following these patterns beautifully. And if there's no nanowires, and then these axons and neuroids are really growing randomly or so. So what Vinnie does is that she does this so-called calcium imaging. She puts a calcium dye, and then as and when the action potentials are fired by these neurons, and then these calcium ions are passing through these ion channels, and then the fluorescence of these calcium dye is dependent on the amount of calcium ions which are available there. So then she tries to take a correlation maps between if this neuron is firing what's happening to this neuron and this neuron and this neuron, and then this astrocyte and other things, so that you can be able to learn about what type of communication taking place between the neurons also. So it really compares these ones also, neurons grown on nanowires and also neurons grown on plain glass substrates, which normally typically the neuroscientists use, so that you can be able to compare with what's the standard technology to our new things. So really, again, to cut the long story short, and then when you grow these neurons on glass substrates, and then you can see that the fluorescence change in fluorescence as a function of time, and these neurons are all firing randomly. And you see very little correlation. But when these nanowires are grown on indium phosphide, you see all these neurons are firing at the same time, showing that there is some sort of a synchronized and correlated activity is taking place, and you can see excellent correlation coefficient. So when Winnie presented his work at a neuroscience conference and in Melbourne, and then some other neuroscientists were asking, what type of neurons you're growing, and then she mentioned that she's using rat neurons, and they said, why are you wasting your time? And how about using stem cells? So now we got a project funded by the Dementia Australia and Ilgilbar Foundation, and there we are working with stem cell biologists and then neurobiologists, and so also artificial and computer scientists using deep neural networks or so. So what essentially we're also developing some nanoscale electrodes so that we're able to measure the signals very nicely here. So here what we're doing is that we're taking the stem cells from the Alzheimer's patients and healthy people, and then try to see the signaling behavior between both of them, and so that you can develop the algorithms and using deep neural networks or so, and so that you can do the stimulation of these neurons by using the algorithms from the healthy people, with the hope that we'll be able to do the stimulation or so. Also, you'll be able to really measure the signals from these brain and other things using these nanowire electrodes and other things. And again, it's a really great project involving University of Melbourne and Monash University and Wollongong University and ANU. I'm learning a lot about neuroscience also because I know very little about it. In conclusion, nanowires open up opportunities for manipulation of light matter interaction at the nanoscale and developing new class of nano lasers and nanowire lasers and LEDs. And I demonstrated terahertz detectors, but I didn't have time to talk about terahertz modulators, integration of our nanowire lasers, also optoelectronic devices on various platforms, and also nanowire solar cells, and engineering the growth of the neuronal networks also. And again, once again, I want to thank our funding agencies and leave you with some information about our journal, and then applied physics reviews, which has got an impact factor of 17 plus or so, and we only publish very small and high impact papers or so. And then also I mentioned to you about the potential PhD and postdoc positions, and please keep an eye on this one. And also that my wife and Vidya and I have started an endowment to really help and support the students from developing countries to come and spend some time in ANU physics, so that they can really develop their networks and also learn, and then also be able to really make use of high-tech equipment and other things as well. With that, and of course this for the last year and this year we'll not be able to have anybody, and so because of the COVID, and then maybe in December 2020 this year, if you can apply for 2022 round, and again here's a website for that particular one. Particularly we're targeting master students and final year of the 5-year engineering students or so sort of thing, so that they get the research experience, so that they'll hopefully get excited by research and then really pursue research as a career. So with that, I want to thank you for your attention, and I'm happy to answer any questions you may have.
Thank you very much, sir, for a wonderful talk and briefing the outstanding work that you do back in Australia. So I have received a couple of questions in the chat box, and let me brief them out. And one question is, what is the possible time scale for the cathode luminescence that you observed?
So that means you're talking about the lifetimes of the carriers, or otherwise, or a measurement, or so basically these are the CW measurements. So in other words, you scan the electron beam and look at collect all the light which you're getting, and then the lifetimes means we do lifetimes, because the cathode luminescence lifetimes means you need to really have means the so-called beam blanking and other things to be able to make these short pulses of the electron beams, and which we do not have with us. And these are the CW measurements which we're doing, and we do also have some collaborators in other places like in Germany, and where they do these time resolved cathode luminescence measurements and other things, and then we end up collaborating with people like that. And then mostly what we do in our laboratory is time resolved photoluminescence, and then so that helps be able to really do the lifetime measurements. And then we can only measure up to smallest ones which we measure is up to 50 or 60 picoseconds or so. But whenever we want to measure the picosecond lifetimes, we go to Oxford University, where they do the so-called the terahertz, the optically pumped terahertz conductivity measurements, and it also gives you the lifetime of the carriers and other things as well, sort of thing. And also we work with our colleagues at University of Cincinnati, Again, they do the time resolved photoluminescence measurements. And these are all done in the single nanowires, not ensembles. So which is challenging, and that really makes it exciting to precisely quantify these things.
Okay, so another question, could you please comment on the theory behind how these nanowires manage to overcome the lattice mismatch?
Okay, so that's a good question. That's a challenging question and a good question. So really, basically what happens is that two things what's happening. Basically, because of the three-dimensional nature, so then what happens is when you got a two-dimensional material, always you have to know you got a constraints, right? They're attached to this substrate. That means if they want to expand, and the only way they can expand is due to creating dislocations or creating dislocations. That means either you really get rid of some atoms and create dislocation, or a sort of thing, for example. So that's why you end up creating these so-called, dislocation formation and all these things, for example. Misfit dislocations, we call them. In the case of nanowires, what happens is first and foremost, they're really expanding laterally because they're really coming out of this one. So those constraints are there, but also because at the nanoscale, you're able to really do that. But if you go to larger scales, again, you end up creating dislocations and other things. And so that means you really need to optimize these conditions in order to be able to grow these ones as well. So it's again, this is a challenging issue. And then that's, I think, we're able to, in fact, we used to think that we'll never be able to grow defect-free nanowires, which are really larger diameters, which are needed for device applications like lasers and solar cells or so. But as I mentioned earlier, that we were able to demonstrate nanowires as big as 700 nanometers, and then able to really show that they're excellent quality and then there are no defects. And one of the major challenges is the twin defects, which you end up having. And again, those twin defects, you need to optimize the growth conditions. And what should be the temperature, what should be the 5:2 ratio, and all these things. So that's where students end up spending a lot of time. For example, Ashwini, who's from KUSAT and from your place, and then she is working on growing these nanowires on flexible substrates like graphene, also mica, and all these things for flexible optoelectronics applications. And again, try to understand the nucleation behavior and be able to get a good quality nanowires, also vertically aligned. But lots of times, you don't get all the time these vertically aligned ones. Some of them are going in a particular direction, some of them are crawling on the surface and all these things. You really need to find a good growth window in order to be able to do that. And that's, again, the good students make all the difference, and the hard work and persistence and perseverance is an important part of research.
Sure. Okay. So also, you mentioned about the possible application of these nanowires in solar cells. So could you please comment on the stability of these nanowires when they used in solar cells? I mean, thermal stability probably.
Okay, thermal stability is not a major issue because these are all very good materials. So for example, if you're dealing with things like perovskites or something, you have to always worry about stability and all these things, because essentially, what I mean is these are, three-phase semiconductors are well known for stable things. We're using them for lasers and solar cells. In fact, some of these, three-phase semiconductors are used in these concentrator systems where 500 suns of sunlight has been focused on these solar cells. But of course, you need to worry about the heat dissipation issues in those sorts of intensities. And then that's why they've got a cooling systems and all these things. Of course, that's why there's a big thing. But in this case, it's not a major issue. And but at the same time, again, depends on what you're doing. But again, you also need to, for example, if I'm talking about flexible solar cells and other things, and you're embedding, hopefully, if you can embed them into polymer materials, which have got a higher thermal conductivity than the poorest thermal conductivity materials, and all those things you need to really worry about. Heat dissipation is the most issue in any devices. So that's something which you always worry about as well.
Okay, so thank you very much, and I haven't got any other questions. And let me thank you once again for joining us for our celebrations. And thank you very much. And Pramod sir can brief if he would like to add something on top of that.
Thank you, Professor Jagadish, for a very excellent talk. I think our research community has really enjoyed your slides and your information, which has been passed through to them. We hope to have some joint collaborations later on. We'll discuss on that later.
Sure.
Thank you.
Okay.
Thank you for joining us.
Thank you very much for inviting me. And then thank you, Professor Pramod Gopinath and Professor Shinu and Professor also Dr. Praveen as well. Thank you all of you. And it's been a pleasure talking to all of you. And good luck to all of you. And congratulations again for your 25th anniversary or the silver jubilee of your school. Thank you very much.
Thank you very much.
Professor Girija Vallabhan has also informed that he had watched it live in YouTube.
Okay, good. Thank you very much. And please, thank you.
Okay, thank you so much.
Thank you, sir. അവസരം പോവാലോ അല്ലേ?